Okay, so we've seen a good start on the processing, how things go in and out of RAM, moving from a single line serial communication to parallel communication through registers, the basic idea of applying logic gates to get some processing between an input and an output. There's another big point that goes with that word that we haven't touched on yet, the processing. We need to do some math. Right? We need this machine to do math for us. So that's what we're going to look at today. Machine math. I'll put that after the label. This playlist kind of started off with what a logic gate was. That's our main component for controlling whether we have a 1 or a 0, whether our 1 or a 0 input becomes a 1 or a 0 output. So in particular, machine math, we're going to we want to do math with logic gates. How do we put logic gates together in such an order that they will do math? So that's our topic for today. So let's get started into that. Okay, so we're going to do some math with logic gates. And we don't want to build a circuit for every operation in math. Right? That's going to get very complicated very quickly. And circuits are kind of physical devices. So if we have a bunch of complicated circuits, there's a bigger chance something's going to break. So we want to kind of minimize that into the simplest circuit we can get. So we want to try to find an operation that we can build everything else from. Kind of like we learned in elementary school, right? Way back then when we're young, we start with counting, and then we go from counting into addition, and then we go from addition, we add subtraction, and then we build multiplication, division, and everything else from there. So we'd like to find one we can build from. So let's look at those first two, addition and subtraction, and see which one seems like it might make a better circuit. So add and subtract. And for those who maybe stumbled across these videos on the internet, this playlist is supplemental material for a class that I'm teaching in fall of 2020. So I'm going to mention a couple things here that are, kind of briefly review the theory. If you're not familiar with it, I will include in the comments or something a link to the actual lecture, because I'm teaching the class and we go over all the theory there. And then these supplemental videos are just to see that theory applied. So that's why some of the theory part might seem very brief here, but I'm going to mention, in particular, 2's complement. If you're not familiar with 2's complement, I'm just going to mention it here. So you might want to check a video on that. Check a video on the theory behind 2's complement. If you're vaguely familiar with it, though, the brief mention here will show how it works. So getting into adding. So an example of adding, let's take 4 plus 5. Those are some easy numbers to add. We'll carry through all our process. So in binary, 4 is going to be 0, 1, 0, 0, and 5 is 0, 1, 0, 1. So to add them, we would do just like we did way back in elementary school, writing things on paper, and we just take it one column at a time, right? Only we're in binary, so our only symbols are 0 and 1. 0 plus 1, well, that's easy, that's 1. 0 plus 0 is going to be 0. 1 plus 1, that's 2, which in binary, 2 is 1, 0. Takes up 2 columns. So 1, 0 is a 0, and then we have to carry the 1 over to the next column. Now 1 plus 0 gives us 1. So 1, 0, 0, 1, that's 8 plus 0 plus 0 4s plus 0 2s plus 1 1. 8 plus 1 gives us 9. Right, what we would expect from a 4 plus 5. That's kind of messy. Gives us a 9. It's exactly what we would expect. And looks like we're just taking those things and combining them. That shouldn't be too difficult to do a logic gate. And have to carry a bit at some point. But something out if we need to do that. What about subtraction? Let's take 9 minus 3. Again, easy numbers to work with. We have 9 right there. So 1, 0, 0, 1 minus 3, which is 0, 0, 1, 1. So 1 minus 1, that's it. Using the integers first. So 1 minus 1, don't give us 0. We know that. 0 minus 1, we can't really do that one. We have to borrow from another column, just like we did using base 10 math way back in elementary school. Right? Take it one column at a time. If we don't have enough, we have to borrow from the next one. Which we don't have anything there right now, so we have to come 2 columns over and borrow stuff. So that's going to leave a 0 there, but we borrow from the column size. Right? We're in base 2, so we borrow our base. So when we borrow from the next column, we borrow a 2. Right? Way back in elementary school, when we were learning decimal numbers, we're in base 10, so we borrow a 10, and that adds a 1 to that column. Well, same thing here. We're in base 2, so when we borrow 2, which is a 1, 0. And that puts something in that column. So now we can borrow from a 2. We'll borrow one of those, which leaves 1 behind. And then now we have 1, 0. So we have 2 here. So 2 minus 1, we can do that. 2 minus 1 is 1. Then over here, well, after we finished all of our borrowing, we have a 1. 1 minus 0 is 1. 0 minus 0 is 0. So then we have 0, 4s. Oh, that's 8. We have 0, 8s, 1, 4, 1, 2, and 0, 1s. So 4 plus 2 gives us 6. Exactly what we would expect. So that gives us 2 operations we can use. That borrowing looks like it might be a little complicated in the circuit. So that's where 2's complement comes in. Because 2's complement gives us negative numbers. So then instead of subtracting, we can use 2's complement to add the negative so that we only have this combination one, right? All we're doing is adding 2 numbers together, and sometimes we have to carry a bit. So 2's complement switches subtraction from its own individual operation into adding the negative. So let's do this as 2's complement. And 2's complement, well, we'll keep the 9 the same. 1, 0, 0, 1, 9 minus 3. Which I guess I could write as 9 plus negative 3. Let's write it that way. So to 2's complement it, well, we start with the binary. And then we'll complement that. And complement in binary is easy because we only have 2 symbols, so the complement is the other one. So the zeros become 1s and 1s become 0s. 1, 1, 0, 0. And that gives us the 1's complement. So to get to 2's complement, we'll add 1. Add 1 to that. Then our 9 hasn't changed. So the 9, let me come down here and write this because I'm getting over there at the edge. So our 9 is still 1, 0, 0, 1. So here we complemented the 3 and then added 1 to get to 2's complement. So now we have a negative 3 represented by 1, 1, 0, 1. So instead of subtraction as being its own operation, we're going to do add the negative. And 1 plus 1 is going to be 0. Or 1 plus 1 is 2. In binary, that's 1, 0. So it's a 0. We carry a 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2 again, so which is 0. We carry the 1. And in 2's complement, we always have an extra bit. When we do this, we'll always have an extra bit, so then we just disregard that last bit. So again, you can see we got back to 6 by adding the negative rather than having subtraction as its own thing. So we'll use this 2's complement, and that way we only have one operation that we have to build in our logic gates. We just need something that adds. we need to put together some logic gates so that they will combine a 0 and a 1 to give us a 1, a 1 and a 1 to give us a 0 and a carry bit, and a 0 and a 0 to give us a 0. And that's all our combinations. So let's get started looking at how we build that with logic gates, and then we can use 2's complement, which the circuit that does that is the same circuit that we use to find 2's complement. So then that takes, that old saying, 2 birds with 1 stone. So we can use the same thing to find 2's complement and then use that to add. So let's start looking at that circuit, building up that circuit to do this for us. So let's start by putting together our truth table here. So that way we can refer to it as we build up the circuit and see what we need. So let's put together what we need in our truth table. So we're going to have a couple of inputs, obviously the 2 numbers we want to add. We're going to come from our control unit, serial communication down to a register, where we can split that number up and deal with it 1 bit at a time, right? So if it's, we have 1 byte holding our number, say, we can split that up in a register and deal with each bit in that byte as its own column. So we'll need 2 registers, although we're only going to talk about 1 column, but this would repeat through the whole register, right? If we have 32-bit registers storing 32-bit integers, it would do this. We would just do this for each bit in the register, each column. So we're going to need 2 registers. I'm going to call them A and B. That's the 2 numbers we're adding. And then we had a carry bit, right? We might carry a bit from the previous column. So we might have a carry bit come in as an input. And then, like we saw when we added those up, so here's our inputs. We have A and B, the registers holding the numbers where we want to add together, whether one might be adding them or might add the negative, right? Or if it's 2's complement, the number, we flip all the bits, we run through an inverter to flip all the bits, and then we put a 1 in the second register. So that gives the 2's complement number. But the 2 numbers we want to combine, I should stop saying add because we're doing this to get adds. We're doing this to get addition. So I'm going to say combine. So the 2 numbers we want to combine into an output. And then we might have a carry bit coming from the other column. That's our inputs. And then for outputs, we'll have a carry, because 1 plus 1 gives us 2, which means a 0, and we carry a 1 over to the next column. So we'll have a carry bit or the column bit. I'll just label them like that. And I'll come back and put some, and then this will give us our truth table, so we can trace that through as we build the circuit and make sure we're getting the right thing from each combination of inputs. So how many combinations do we have? Well, when we build a truth table, we'll always have 2 raised to the number of inputs combinations that we could have. So in this case, 3 possible inputs. So that means we'll have 2 cubed inputs. So we have 8 possibilities of combinations. So my method of keeping this organized is I figure out how many combinations we have. And then in the first column, I'll do half of them as zeros and half of them as ones. Just a systematic method to make sure I don't miss anything. And then the next column, I'll cut that in half. Do 2 zeros, 2 ones. 2 zeros, 2 ones. Then the next column, cut that in half again. 0, 1, 0, 1, 0, 1, 0, 1. And that's just a good systematic method I use to make sure I don't miss anything. So figure out how many there are. The first column gets half zeros, half ones. Then however many that is, in this case 4, cut that in half to the next column. 2 zeros, 2 ones, 2 zeros, 2 ones, and keep going like that. Cut it in half again. In this case 1, 0, 1, 0, 1, 0, 1. And then that gets all the combinations in a nice systematic order so don't have to worry about missing things. So now we're adding these. Okay? So 0 plus 0 plus 0, well, that's 0. So we have a 0 in our column and a 0 in our carry. 0 plus 0 plus 1, 1. So 1 in the column, 0 in the carry. And the next one, 0 plus 1 plus 0, we'll get the same thing. We're not carrying anything, but we do end up with a 1 in our column. 0 plus 1 plus 1 gives us 2, which in binary is 1, 0, so we'll have a carry bit and a 0 in our column. 1 plus 0 plus 0, again we're back to 1, so 0, 1. 1 plus 0 plus 1 gives us 2, 1, 0. 1 plus 1 plus 0, we're still at 2, 1, 0. And then 1 plus 1 plus 1, well, we're up to 3 now. And 3 in binary is 1, 1. So we have a 1 in our column and a 1 in the carry. So that is all the combinations we need our circuit to do. So I'm going to go ahead and put the truth table up here. That way we can refer to it, refer to what needs to happen while we're diagramming out the circuit. And we're only going to do one column. You'll especially see it when we get over to the example scene later and see how many wires are involved for one column of this. And then expansion of it is just doing it, however big our registers are. If we have 8-bit registers, that means we need to do this 8 times. 16-bit registers, we got to do this 16 times. So the same thing just gets repeated to expand it up. But we're just going to look at one column, and when we see it on the breadboard with wires, rather than looking at a little integrated circuit and just knowing that this stuff happens on the inside, you'll definitely see why I'm only doing one column for the example. So first thing here, let's list our inputs. So we have register A and register B, holding the two numbers we want to combine. The control unit's going to send them down serial communication to the register, where the register just holds them and goes from serial to parallel communication, and then in parallel communication we can deal with each bit in that chunk of data one at a time, whether we have a byte or word, however big our register size is, we can deal with it one bit at a time instead of the whole thing at once. So we have two registers holding our numbers, and then we might have a carry bit coming from another column. So how do we combine them? I'm going to start with the numbers. So I'll bring over A and B, and we need a logic gate by which we combine our bit from A and our bit from B. So we need a 0, 0 to give us a 0. Any of our gates will do that, so we're good on 0. Well, I guess we kind of rule out a Nand gate that way, 0, 0. So we need, most of our gates are going to give us 0, and 0 will give us a 0. We need a 0 and a 1 to give us a 1. So that rules out an AND gate. OR gate's going to work. But then we hit a problem, because we also need 1 plus 1 to give us a 0, and then we'll take care of the carry bit elsewhere. So 1 plus 1 returns 0, can't use an OR gate, we'll need to use an XOR gate. XOR will give us 0 combined with 0, gives us a 0. 1 combined with 0 gives us a 1. 0 combined with 1 gives us a 1. And 1 combined with 1 gives us a 0. Exclusive OR. One or the other, but not both. So to get our column bit, we'll need an XOR. But then we need that carry bit. And that means we need, along with this, we need that situation where they're both 1. So it gives us a 0 through the XOR, but a 1 in the next column. And the gate that will only give us a 1 if we feed in 2 1s is an AND. So then we'll need an AND gate to get the carry. So that's kind of the first starting point. So let's see, I'll jump over this line, come down into an AND gate. So an XOR, exclusive OR, and an AND gate will give us what we need to combine them in the right order. 0 and 1, or 1 and 0 will give us a 1. 1 and 1 will give us a 0 with a bit in our carry column. And that's the essence of it. But we need to do that again, because we have this carry bit coming in. We could be carrying a 1 over from the previous column. So I'll dump this over here, bring it over here, and we have to do this whole thing again with our carry bit. So we will either feed through an XOR to figure out what's in that column, and then that will tell us the column bit. Oh, another line for an XOR gate. So an exclusive OR to get the column, but then we're also going to bring both of those down and through an AND gate. This whole thing again to see if we have one that carries over. And then that carryover, well, it might need to combine with these. And if it does, well, then we just need an XOR gate. Once again, we can run through an XOR gate to see if we need to combine those. And the most we're going to have in this situation, as you can see from the truth table, is 1, 1. So we don't have to worry about hitting 4 and needing another carry bit with this. You might want to pause the video and make sure that makes sense. And then those two AND gates, we'll run those through an XOR to see if we need to combine them. And that tells us if we have a carry bit or not. So that is the circuit for how machines do math with logic gates. Combine numbers. So it's basically adding. If we feed in two positive numbers, it's going to run through here and add them. If we feed in a positive and a negative, it'll run through here and combine them with add the negative, which is subtraction. And then from there, we can build up multiplication, division, do the modulus, disregard some of the bits to separate between floating point division and integer division and modulus. But we can build it all from this circuit now. And that's what we need. So a couple XOR gates, 3 XORs, and 2 AND gates is what we need to do math, do a column of math. So again, we take our numbers from the registers, look at the bits in that column, and if there's a 1 and a 0, that triggers our XOR bit, so we have something in that. So we have something there, but 1 and a 0 is not going to trigger our AND gate, so we have a 0 there. And then we just have to check that column with the bit we carried over from the last one to see if we're going to have another thing that we have to carry over and combine in our other column. So let's trace these through to make sure all that works. You might want to pause the video and look at that picture and make sure that makes sense, because that's all it takes. Okay, so I was originally thinking I would go up here on the board and write a bunch of 1s and 0s all over the schematic, trace that through, then go over and see the example, and kind of see the same thing. But it's starting to feel like this is running a little bit long. I haven't checked, but from filming the scenes so far, it feels like it's starting to run a little long. So let's just look at it in the example where we can see the column and carry bits with LEDs. So to build that, I'm going to use, which one do I have in my hand here? So this is, will it show up here? Not really showing up. A TI 74 LS86 that has 4 XOR gates. And you can see from the schematic, we need 3 XOR gates, so that chip will work for that. And we need 2 AND gates. So to do that, I'm going to use a Texas Instruments 74 LS 08, I think. Yes, 08. 74 LS 08 has 4 AND gates, which is plenty enough for this. So I'm going to go hook up these 2 chips and get an example ready. Then we'll look at that, trace the truth table through with some LEDs so we can see that this is working instead of doing it on the board and the example mode. So I'll be right back with that.
Okay, so here's this circuit hooked up. You can see there is a bunch of wires. So summarize it. Each one of these, when I was putting it together, I was thinking the greens, like register A, like we drew on the picture. Oh, and I copied the what was on the board onto a piece of paper to refer to that. So greens like what's in register A, the yellows what's in register B, and the red is what is considered the carry bit, just to match up what was going on there. So then come down here, kind of hard to see there, but a couple green wires, a green wire and a yellow wire come over here to the 74 LS86, the XOR gate, and they feed into the XOR and the 74 LS08, the AND gate. So A and B feed into XOR and an AND, so that's here on the picture. Then the output of that XOR feeds into, that's these two white wires here, feeds into an XOR with the carry bit, which is the red wire here, or into an AND gate with the carry bit, again a red wire. Then those outputs come over here, and the green light is our column, and the red light, the red LED is our carry bit. So let's just trace through this and see all of these working. So first off, all zeros, and I already have all this mess, so I just bypass switches and buttons and stuff, and I'm just gonna plug it into ground for a 0, plug it into the hot rail for a 1. So all zeros, neither light is on. We get 0 for the output. Then the next row here, zeros in our registers and a 1 on the carry. So let's move the carry bit over to the 1, and we can see nothing in the carry and a 1 in the column, which matches our truth table. The next we have A is 0, B is 1, and C is 0. So move the carry bit back down, move the B up into a 1, and again we can see 0 in the carry, 0 in the carry, 1 in the column. The next one is going to be 0 in A, a 1 in B, and a 1 in C. So if we move the carry bit up here, well, now we can see we have a 1 in the carry bit and a 0 in the column. That matches our truth table. Next up, we have a 1 in an A, 1 on A, and zeros in the others. And we can see nothing in the carry and 1 in the column. So where are we at now? 1, 0, 1. So let's move the carry bit up to a 1. So carrying a bit over, having a bit in register A and a 0 in register B gives us a 1, 0. Matches our truth table. Next we have A is 1, B is 1, C is 0. So move the B up there, the C down there. And again we have 1, 0. 1 in the carry, none in the column. And then the last row here, all 1s. Everything's got a 1 coming in, so we move our carry bit from the previous column up here, and our output is 1 in the column and 1 in the carry, which matches our truth table. So that's the circuit in action, and so you can see that's how we add with logic gates. So let's go back over to the board and kind of wrap this up.
And so there it is. That's one of the ways we can combine logic gates in order to do math. And in this case, we build up addition. So like you probably learned in elementary school, once we can do addition, then we take that addition and expand it to subtraction, or computers are really, really fast, so we can just do the, add repeatedly to get multiplication and subtract repeatedly to get division. And computers can do that lots and lots of times really quick, so then they're doing that we don't need shortcuts for the multiplication. We can just add lots and lots of times, and the computer's going to do it so quick that it still seems speedy to the human. One of the ways to do it, there's more than one, obviously, but built-up addition, and if you're building a computer, wanting to see one from scratch, you're probably going to buy a chip that has a piece that does the math. This is just kind of an explanation of how that works, unless you just want to build one. Right? It's kind of a fun little thing. You're interested in it and find it interesting, and you want to actually plug one up and see it work. So that's kind of why I know how to do this. Otherwise, you're probably going to buy a chip that already has this stuff in it, and then we just activate that circuit. But that's how it works, and there's obviously more than one way to do it. You know, putting that together can be a fun little puzzle too. You know, it's like solving a puzzle, figuring out what we need to make that happen. It can be a lot of fun. That's why I know how to do this. I was curious, so I sat down and thought it through until I figured out a way that worked. But that's one way to do it. So then our machines can do math, and hopefully it's not mysterious anymore. You know, it's not just something the computer does. You can actually now take the knowledge from the lectures, expand it a little bit more, and actually see how the machine is combining things to get math, and addition in this case, and then we can build addition and subtraction when we add the negative. And then from that we can build multiplication and division and get all our math done. And it's not something mysterious, it's just some logic gates. And remember, our logic gates are just a couple of switches. That's just a way that we can put switches, on and off switches together in order to make things happen. So hopefully that cleared up some of what that is. It's not a mysterious piece inside the computer anymore. You can actually see how that works.